Hi, everyone. Today's lesson is a pretty important one for the rest of this unit. Today, we are learning a new method of counting that we use commonly in chemistry, which is called the mole. So if you need to come back around to this lesson, please rewatch it as many times as you need. As I said, this is a pretty foundational one for what we're doing for the remainder of this unit. So, the first thing I'd like to sort of talk about with you is something that we've mentioned before, qualitative and quantitative analysis. So, we've talked about this in the context of observations that can be either qualitative or quantitative. What I'm describing here is a qualitative or quantitative analysis. So, identifying whether a certain substance is present in a sample. So, very similar concept. When we're looking at qualitative analysis, we were identifying a substance without using any measurements. So, very similar to what we would talk about as a qualitative observation. Um, Likewise, with a quantitative observation, we are looking at things that are measurable. And likewise, here, a quantitative analysis is the process of measuring the quantity of a substance in a sample. So, it provides us a numerical data. So here I've put two examples also in the textbook. The first one, which is a urine test, this is just identifying whether or not there is high glucose in a sample of urine. So this would be used for people who are trying to identify if perhaps they might be diabetic. So in here, we are using just a test strip. So we're not actually coming out with a number. We are just testing for the presence of high glucose. Okay. Likewise, on the other side, we've got an example of a quantitative analysis. This is a glucometer. This is a device that people who are diabetic use to test their blood concentration for glucose. So they're identifying, again, an actual number, an actual concentration of glucose in their blood. So, wanted to just speak about this a little bit because what we're dealing with today and what we're starting to talk about with this unit is using quantitative measurements. So, actually, measuring a number of particles, for example, and that type of idea. So, that brings us to talk about the mole. And the mole in this context is a unit of counting. So, I want us to look at a couple of sort of familiar examples. Here is a balanced chemical equation for the reaction between hydrogen gas and chlorine gas, which produces HCl gas. So, just looking across this, what this tells us, almost like what we would write as a sentence. So, what we see here is that one molecule of hydrogen reacts with one molecule of chlorine to produce two molecules of HCl. Okay, so we are familiar with this already. Now, I wanted to just show a little picture so we can sort of visualize it. When we're talking about H2, for example, we're looking at two hydrogen atoms that are actually chemically bound to each other. We talked about this in Unit 1 quite a bit. So that would look something like this if we were thinking of what the molecule looks like. Okay, and likewise, our Cl, right? They're actually linked together. And so for each one of these molecules that we add together, we end up with two of HCl, which would look something like this. Okay, so this picture is depicting what that reaction looks like. But the point I'm trying to make here is that we see that this is happening in, the same ratio every time. 1 molecule of H2 is needed to react with 1 molecule of Cl2 to make these 2 HCl. And we know that by balancing the equation, okay, which we've done many, many times already. Also going back into even grade 10, right? We learned about balancing and why that was so, so important. So going on from there, what does this have to do with this mole concept that I was mentioning before? The mole is what we call a chemist's dozen. So it is an example of a common counting unit that we use in chemistry. So I've put a video right here, which I am going to show in class. You're welcome to go back and watch this video again. It sort of explains it in a visual way. But I wanted to go over just some common counting units that we have just in everyday life. So here's an example, 1 dozen. Okay, 1 dozen, when we say that, it commonly means 12 of something. So if I go to Tim Hortons and I order a dozen donuts, I'm ending up with 12 donuts. Okay. Likewise, you might know this one, a ream of paper. Okay, that's like a little packet of paper that's you buy in big boxes and things like that. 1 ream of paper has 500 sheets of paper in it. Okay, so if you went to Staples and you asked for a ream, the employee would understand that ream to be the 500 sheet size. Okay, likewise, 1 hour, that's a really common unit of measurement that we all use. That represents 60 minutes. Right. And so we're all sort of comfortable with using these in regular conversation. And so, chemists, we also have a method to describe things, which is called a mole. Okay. Now, of course, chemists are interested in things that are extremely, extremely small. Okay. Thinking of atoms and molecules, things we cannot see or count with the naked eye. Okay. And so we need a special way to count them, which we call the mole. Okay. And the mole is representing a specific amount of a chemical substance. And we will see shortly how we use the mole, but I want to introduce you to a couple of really important values. So again, we're talking about extremely tiny, tiny quantities. It's much easier for me to understand a mole as opposed to using really giant numbers. So here's an example. 1 mole of a substance contains 602, this number is crazy big, 23 zeros, 23 decimal places. This is known as 602 sextillion. Okay, it's a huge, huge, huge number. So again, working with huge numbers, that can be challenging. So we're going to actually use more so is the scientific notation version, 6.02 times 10 to the power of 23. Okay, and again, this number is way easier for us to use. It's in scientific notation. We don't have to worry about writing all of these zeros every single time. Okay, so this value, this 6.02 times 10 to the power of 23, it represents number of entities, and we call this Avogadro's constant. And sometimes we call it Avogadro's number as well. You'll hear that used interchangeably, Avogadro's constant or Avogadro's number. And I mentioned right here, the symbol for this is N with a small a beside it. So capital N and as a subscript, an A. And I will show you how we use this in an actual question in just a few minutes. So this number or this value is determined experimentally. We're not going to go into the experiments that actually found this number out, but it is equal to the amount of substance that contains as many entities. Another name for that is atoms or molecules, as there are atoms in exactly 12 grams of carbon-12. So we spoke about previously in the course, we often use carbon-12 as sort of the standard. And the reason why we said that is that carbon-12, the isotope, is very, very close to 12.00. Okay, So when we're using the mole, we're going to have, again, a symbol that we use in our calculations. The symbol we're going to use here is a lowercase n. That represents number of moles. Okay. The unit for moles is something new we haven't seen before. MOL. Okay, so MOL represents the units for moles, and we're going to practice using that very, very soon. So I wanted to include some visuals for you, some visuals that show different moles of a substance. So on the left side here, we're showing 1 mole of carbon. So 1 mole, as I said earlier, that is a method chemists use to describe 6.02 times 10 to the 23 atoms. Again, that's 602 sextillion atoms. Way easier for me to describe this as 1 mole as opposed to describing this as 6.02 sextrillion. That's a huge, huge number, lots of zeros after that. Okay. Likewise, right beside, I'm showing 1 mole of sulfur. And 1 mole of sulfur, again, 6.02 times 10 to the 23 atoms. But you can see that it takes up more space because the atoms are not necessarily the same size, and they're definitely not the same mass, okay, which I'm showing down at the bottom. So 1 mole of carbon is actually 12.01 grams. We can measure that quantity. Likewise, if I did the same thing with sulfur, I could take 1 mole of sulfur. That would weigh 0.06 grams. Okay, so this is a quantitative value, something that I am counting. Again, since the atoms are different, which I'm going to show down here, the atoms are different, the volume and the mass they take up is different. Okay. However, using our method of the mole, we can still describe each of these things as 1 mole. Here's another example. If I described 1 dozen donuts, okay, 1 dozen donuts, it would be representative of 12 donuts. That's a common way that we can count that. But what if I wanted to count, let's say 1 dozen grains of sand? Right? Those are very different sizes, right? Those are very different things. The 1 dozen donuts, it takes up more space. It's going to be a lot heavier, but I'm still using the same unit of measurement. So that's the same thing I'm doing here with moles. I'm saying 1 mole of carbon as compared to 1 mole of sulfur. Okay. To extend that a little bit further, the picture on the right side. This picture is showing 3 different substances. We've got sucrose, which is just table sugar, sodium chloride, and carbon. All 3 of these each contain 1 mole. Okay, again, 1 mole represents 6.02 times 10 to the power of 23 entities. Okay, so if we're talking about sucrose, it would be 6.02 times 10 to the 23 of those sucrose molecules. Table salt, 6.02 times 10 to the 23 NaCl of that ionic compound. And likewise here for carbon, 6.02 times 10 to the 23 solid carbon atoms. So again, we're using this unit of measurement, 1 mole, because it's way easier to communicate with people than to continuously be using this huge, massive, massive number. Okay, so next up, we're going to see a couple of examples of this. So for example, a question could say, how many atoms are in 1 mole of carbon? Okay, again, 1 mole represents 6.02 times 10 to the 23. In this case, carbon atoms. Now, in this context, atoms would be the entity, okay? However, I could still also be asking about molecules. So let's say I had 1 mole of H2O, 1 mole of water. Well, that's still 6.02 times 10 to the 23 H2O molecules. Okay. Now, Avogadro's constant is a huge number because it allows scientists to group atoms and molecules into convenient amounts. Again, a mole is way more convenient, especially when we're trying to count atoms and molecules. Those things are extremely, extremely tiny. We cannot see them with the naked eye. So the mole is way more convenient for us to use as chemists than to write out this big, long number of molecules or atoms every single time. So, we're going to move into is looking at the relationship between these different things. So, relationship between N, N, and Na. I know that looks really confusing, but we're going to put names and put sort of, some practice into using these different things. So, capital N in this context, it represents the number of particles. So, as I said before, the particles could be number of atoms, molecules, etc. Okay, depends the context of the question. So we'll see some examples of that afterward. Small lowercase n is number of moles. Okay, and Na capital, that is Avogadro's constant. Now, what's nice about constants is that they never change. Okay, so you've seen constants before in math, you've probably seen them in physics if you're taking physics. A constant is an unchanging value. So Avogadro's constant always is 6.02 times 10 to the power of 23. Okay, that is a constant number. So whenever we see Na capital, we're going to be plugging that number in. Now, down below, I've put in something that some people find helpful when they're thinking of actually using this equation. I'm going to show you a method where it might not be super necessary for you to actually use the equation, but you can still use it while we're practicing. If I wanted to go between particles and moles, I would times or multiply by Avogadro's constant. If I wanted to go the other way, from the number of moles into the number of particles, I would divide by Avogadro's constant. So we're going to see this in practice in just a moment. Another way this same information, the same concept could be written is that the number of moles, lowercase n, is equal to capital N, number of particles, divided by Avogadro's constant. So all of these different ways are really just describing the exact same relationship. It's just sometimes more convenient to use one version of the equation over another. So this will include and this will require of us is sort of figuring out what we're given in a question and, best choosing the method to solve for our unknowns. So I'm going to show that in an example just below here. So a question might say, how many moles are present in a sample of carbon dioxide CO2 made up of 5.83 times 10 to the power of 24 molecules? So what I like to do with these questions is sort of highlight for myself what the things are that are given and what things are not given. So the first thing I do when I look across the question is that I see that I have a number of molecules. So I'm going to write that number down first. And as we said above, capital N is number of entities. Okay, in this case, we're talking about number of molecules. So I'm going to write that number down first. Okay, and I'm going to include also is the unit of measurement. And here it's molecules, right? This is what I've been given. This is how many molecules I have. So that's step one. Step two, which I'm also going to write just underneath of here, I'm not given this number directly in this equation, in this example, but I know that this number is always a constant, which is Avogadro's number, N capital A. So I'm going to include it here as well because I know I'm probably going to have to use this number for something. Okay. Now, what this actually represents, 6.02 times 10 to the 23, it does technically have a unit as well. In this case, it's molecules per mole. Okay, molecules per mole. So again, in 1 mole of CO2, there's going to be 6.02 times 10 to the 23 molecules. Now, the next part of this is trying to figure out what in the world are they asking for. So I can see in the beginning how many moles are present. And remembering from up top, moles is a lowercase n. So I might put it like this. And I'm thinking about what units this should be in. And as I mentioned before, units for moles is just MOL. Okay. So I've sort of set up here is like my givens, and then I have to figure out, okay, what equation do I use here? Before I do that though, I want to just remind you of something really important about that we spoke about before. I want to look at the significant figures here. So looking at the molecule number and also at the Avogadro's constant, I see in both cases, it's 3 significant figures. And why I'm highlighting that, why I'm talking about that. In my final answer, when I've finished the question, I need to make sure that I'm representing 3 significant figures, no more than that. So it's going to involve some rounding off as we spoke about before. So now I want to try to figure out what version of the equation makes sense for me to use. I'm going to scroll up for just a second here. As I said, I'm looking for number of moles. So when I go up to the top here, I can see I've got a setup right here where I can actually use this version of the equation to help me solve. Now, if you're comfortable and confident doing this, it's totally fine if you started with this and you rearranged the equation. You're going to get the same answer. As I said, this relationship is the same no matter how we wrote it. It's just convenient sometimes to use one version of it over the other versions. So I'm going to go ahead and use this version here. So here's my showing or my, representing the equation that I'm using. I'm going to use the one that involves the number of particles, in this case, number of molecules, over Avogadro's number. Okay, like this. Now, when I'm doing these problems, I like to actually include the units. It's not totally necessary that you do that, but just to show you guys, I'm going to do that because it'll be helpful to us a bit later on. I'm going to plug in the values that I know here, just from what we wrote at the top there. Again, it's not totally necessary that you do this part, but I like to include it because later on it does make some parts of it easier. Okay, Avogadro's number 6.02. You're going to really remember that number after today. Times 10 to the 23. Again, that is molecules per mole, right? 1 mole of a substance, it contains 6.02 times 10 to the 23 different particles. Now, the reason I wanted to write it like this is what this allows me to do is actually cancel units that are the same on the top and the bottom of my equation. So molecules is the same on top and bottom. So I end up canceling it out. And the reason I like to do it this way is because I'm left over with this unit, mole, MOL. And if I go back to what I started with, it's exactly what I predicted I should have. So it's almost a way to check that I've actually used the correct equation. So typing these numbers into my calculator, what we should get, hopefully for number of moles for N, is I should get 9.68. 438, and then a whole bunch of other digits there. Okay, now thinking about this again, I want to make sure I'm representing the correct number of significant figures because, as we spoke about before, there is an uncertainty involved with these measurements, right? I've only got 3 significant figures up here. So just like we talked about in that lesson, I need to make sure in my final answer, I only have 3 significant figures. So what that causes me to do is to look over here and I see 9.68. I know those are significant here. I'm going to actually have to round this one down to make sure that I'm only including 3 significant figures in my answer. So here's how I like the final answers to look. N equals 9.68 with the units. Okay, extremely important that the units are in there. You can put a box around it like this just to show this is my final answer. I would appreciate that because it's easier for me to actually find, but you don't need to write a big sentence or a big statement. You're just putting it into a box like this. Okay, again, making sure significant figures are followed. We can't just put whatever number of decimals that we want. So going back to what I said in lesson 1 of this, you should never be asking me, what do I round this to? Okay, the whole goal about significant figures is that it tells us already in the question, in the values that we've been given. So I hope this video was helpful. I'm going to post it onto YouTube for you guys so you can watch it again and again if you'd like.